Well, this is a presentation video for the mini challenge number 7. A little introduction. The purpose of this challenge is to create two different programs with an open loop controller, one for a square trajectory and the second one for personalized trajectories. Both of them need to take into account perturbances, nonlinearities, and noise. The focus of this challenge is to compare the behavior between a simulated and a real robot.
Yeah, so for the first part, we needed to make a square, a trajectory square that the robot needed to follow. So first of all, for the code is that it starts and then the code initializes the AROSZ node controller and on all the publishers and subscribers. Then we make that the robot needed to calculate angular and linear velocities. So the way that we followed to make this was to calculate the angular velocity required to turn 90 degrees clockwise in a quarter of the time, because it needed to make it like in 4 times of the total time. Also to calculate the linear velocity required to move 2 meters in also the quarter of time. And yeah, so what we've done with this code was to put on a terminal input, like a set point, the required time to make all the trajectories. So time is our set point, and then we make all the calculations of velocity and to the follow this time. Yeah, so also then now that we calculate all the linear velocities, we initialize our AROSZ node, where if it is running, the square trajectory begins, where we put two formulas, where move forward is like the linear velocities, and also the turn 90 degrees velocities. And we made it like half of the time because it's 50% of the time to move forward and 50% of the time to turn 90 degrees. And then the node make the trajectory and publish the trajectory that the trajectory is finished, and then all of the node ends. So for the second part, what the program needed to make was we needed to put points on like a set point, and then the nodes like initialize and make all the trajectory across these points. So yeah, what we done on the code was that we initialize an empty list called coordenadas, and then we make a linear movement function like the last same as the last code, and also we made like a calculate angle and time function. So we needed to calculate the angle and the time required to rotate the robot to face the next coordinates, and we needed to ensure that the angle difference is within pi and minus pi. And also we make another function that needed to rotate to point function. This makes the robot to face the next coordinates using the specified angular velocity and duration of the robot. And then also another function that needed to calculate distance and time function. This way, calculate the distance and time required to move to the next coordinates at a specific velocity. And also we made it like calculating the Euclidean distance. And yeah, so then we make the callback of our coordenadas or coordinates from the custom message that we made on our code. And then now the AROSZ is initializing. So we make all the processing of the coordinates, where we needed to calculate the angular velocity and time required to rotate the robot to face the next point. So it starts to move. And yeah, we calculate the distance and time required to move to the next point, the linear velocity that we point. Now, in our case, it was 0.5 meters per second. And yeah, so move there, and then the robot starts to move forward, and then it iterates this and updates the current position. So the robot knows in which position it is and where it has to be the next position. So yeah, this is how the program works. Yeah. So for the methodology of the results, what we needed to make was to make the export AROSZ master so we can connect to our terminal to the robot. Yeah, so for the Jetson, and also we needed to make sure that on AROSZ we are publishing on the CMD vel our velocity, because that's how the AROSZ node was programmed. And on the real one, it was the smoother velocity. So now we can see the results. So yeah, on the first part, we put like both the robot and on the AROSZ. As we can see, I put like 30 seconds to make it like the robot in 30 seconds. So yeah, actually we can see that the code works perfectly on the AROSZ simulation, like it doesn't make an offset. But on the real one, it starts to make a slightly offset. We believe that it is because it is not precise because of the open loop controller. So yeah, and on the irregular video where we needed to make like the path generation, also I had a set point where I put like all my points. So on a 2 per 2 square, the same that we make the trajectory of the square. So yeah, I put all my points. It is 4 points, X and Y points. And yeah, so the AROSZ simulation started first. But yeah, as you can see, it made the same trajectory, but a bit with an offset on this path. But yeah, it's the same because of the open loop controller. If it is a closed loop controller, it will be precise. And can you change your presentation? Yeah, so the behavioral comparison, an AROSZ it has no noise and a very smooth simulation and no errors, the exact trajectory. And on the real one, also the trajectory path has offset on both parts, part 1 and part 2. And since it is an open loop, it has offset. So yeah, can you change? On conclusions, all that I can say is that yes, so working with AROSZ and on open loop controller, for me and for all of the team I can speak, it is a bit harder because we don't have a feedback to make the calculations more precise. And for me, the calculations was pretty hard, but I can understand that how the dynamic of a robot model works now that I make this code. So I have this learning on my academic formation. So yeah, that's it.